Hi everyone, Nate Solves Problems here, back with another video. In this video, I'm going to try something a little bit different. I'm going to use OneNote to go through the derivation of the kinematics formulas. These formulas are used to solve problems looking at one or two dimensional motion. These are usually the first introductions into physics and just start getting moving, thinking about acceleration and velocity and the premise before forces and everything else. So let's say that we have some ball, some object, whatever you want to be, and it's experiencing some force down. And we're going to say that force is equal to ma. This acceleration is constant, and it's not to be confused with the acceleration that comes in when we're summing up the forces. So, if we're looking at this, we're considering this force moving down on the ball. We're going to sum up the forces. So these are the forces in the y direction. And for the premise of this, we're supposing or assuming that there are no drag forces on the ball. The ball is only experiencing this downward force. So we have the sum of our forces, ma equals that force. That force we're looking at, that ma. So we can see from this the mass doesn't matter. We can cancel it out. The acceleration on the right-hand side does. So we care about this acceleration. That acceleration, we can rewrite it as the instantaneous rate of change of position of velocity with respect to time, or dv dt. And that equals our constant acceleration that we're experiencing from that force. So what we can do is we can separate this differential equation. So we can multiply both sides by dt. And in doing so, we have on the left-hand side dv equals a dt. And we can integrate both sides. We're going to integrate the left-hand side from some initial velocity v naught to some velocity that we could figure out, some velocity v, or v of t, because t is going to be our independent variable here. And we're going to integrate the right-hand side from 0 to t. And in doing so, we have v minus v naught equals a t. Or our first kinematics formula, v as some function of t equals that initial velocity plus acceleration times time. So we're going to take this a step further. What if we want an equation that relates position to time? So what we can do again is we can rewrite velocity. Velocity is the instantaneous rate of change of position, the derivative of position with respect to time. So if we do that, we have dy dt equals v naught plus a t. And we're going to do what we just did. We're going to separate this again. Multiply both sides by dt. We have dy equals v naught plus a t. That quantity times dt. We're going to integrate the left-hand side from some initial position to some position as a function of time. And we're going to integrate the right-hand side from 0 to t again. And in doing so, we get our second equation of motion. This, and I'm gonna write that y of t minus y naught is delta y, just for this equation, equals 1/2 at squared plus v naught t. This can also be written slightly different. If I didn't combine the terms on the left-hand side as delta y, I have y as a function of t equals 1/2 at squared plus v naught t plus y naught, or that initial position. So we have that. We have our previous expression that I wrote in green above as v of t equals v naught plus a t. So we have those two equations so far. Both of them are in terms of time. What if we don't want them in terms of time? What if we say instead our y at some time and our v at some time are our final position, y sub f, and our final velocity, v sub f? Can we write them any different? So if I'm going to rewrite y of t as y sub f and y sub f minus y naught as delta y, and I'm going to rewrite v of t as v sub f. And in doing so, I'm going to solve for time in our equation for velocity, this equation in green, and I'm going to substitute that in to our equation for position. So, if I were to solve for time, I have t equals v naught, or no, that's not, so v sub f minus v naught over a. So what I'm going to do is I'm going to take that and I'm going to plug it back into our equation for position, our y of t equation, which now I'm using the version that I wrote in blue, the delta y equals 1/2 at squared plus v naught t. And I'm going to substitute t into that. So in doing so, I have delta y equals 1/2 a times the quantity v sub f minus v naught over t squared plus v naught times v sub f minus v naught over t. So if I expand that out, sorry, they're not over t, they're over g. Sorry about that. We're substituting in for g, so they're over a. In for t, so they're over a. So if I square the first part and I multiply the v naught through on the second part, this should start to come together. So we have delta y equals 1/2. I'm going to substitute out the acceleration from the first parenthesis that was where we substituted in for t squared. And then I'm going to multiply that by a, so I have a times 1 over a squared, which ends up being 1 over 2a times the equation vf squared minus 2 v naught vf plus v naught squared plus v naught v sub f over a minus v naught squared over a. So I'm going to take that a step further and combine the terms again, and in doing so, if I multiply through the 1 over 2a, I get vf squared over 2a minus v naught vf over a, which that's going to cancel with the v naught vf over a outside of the parentheses. And then I'm going to have v naught squared over 2a minus v naught squared over a, which ends up being negative v naught squared over 2a. So I have delta y equals vf squared over 2a minus v naught squared over 2a. So I can multiply both sides by 2a and add v naught squared to both sides. And now we have a function for vf that we could solve for the final velocity if we only know the change in position, the initial velocity, and the acceleration. So with that, that's our final kinematics equation. We have vf squared equals v naught squared plus 2a delta y. So bringing all of those three back together, we had v of t as well. I'm going to pull that down a little bit more. We had v of t, which equals our initial velocity plus our acceleration times time. And then we had that equation for velocity, or for position, which was y of t equals 1/2 a t squared plus v naught t plus y naught. And that is three of probably the most commonly used kinematics formulas, barring just the average velocity, which is just if you have two velocities, you divide them by 2. It's the average of two numbers. Or also just velocity itself, which is if you have no acceleration, just x over t. If you have an acceleration, you can use one of these formulas. And that concludes it for these derivations. Let me know if you have any questions or suggestions for other videos. Thank you again for watching. Have a great day.